Have you ever wondered why some things seem to move so predictably while others are a chaotic mess? Why a simple lever can lift a massive weight, yet a tiny ripple can send a complex structure into a dangerous wobble? It all boils down to the fundamental principles governing how things interact with the world around them. Principles that range from the elegant simplicity of basic mechanics to the intricate dance of Newtonian physics. Today, we're diving deep into the world of platforms, not just the digital kind, but any system designed to support or facilitate interaction. We're going to compare two vastly different approaches to their design and understanding, the simple platform and the Newtonian platform. While both serve similar purposes, their underlying philosophies, their construction, and their ultimate capabilities couldn't be more distinct. Understanding the pros and cons of each is crucial, not just for engineers and designers, but for anyone who wants to appreciate the hidden complexities and clever solutions that shape our physical world. Let's start with the simple platform. Imagine a sturdy wooden plank laid across two rocks. That's a simple platform. Its design is intuitive, its construction is straightforward, and its function is immediately apparent. There's no need for complex calculations, no elaborate theories required. You see it, you understand it, you use it. The primary pros of a simple platform are rooted in its very nature. Ease of design and construction, this is perhaps the most significant advantage. You don't need a PhD in engineering to build a basic workbench or a makeshift bridge. The materials are often readily available, the tools are basic, and the skills required are minimal. This democratizes construction, allowing individuals and communities to create functional structures quickly and efficiently. Think of early human shelters, basic farming tools, or even a child's treehouse. They all leverage the principles of simple platforms. Cost effectiveness, because of the readily available materials and simplified construction methods, simple platforms are inherently cheaper to produce. There's less need for specialized components, precision manufacturing, or extensive labor. This makes them ideal for situations where budget is a primary constraint, or for temporary structures where a long lifespan isn't a priority. Consider a market stall made of bamboo and tarpaulin, or a temporary stage for a community event. Robustness and tolerance for imprecision, simple platforms, by their nature, often have a higher tolerance for imperfections. A slightly uneven cut, a knot in the wood, or a less than perfect joint might not compromise the entire structure. Their reliance on brute force and direct load bearing means they can often absorb a degree of manufacturing variability without catastrophic failure. This makes them incredibly forgiving in real-world applications where perfect conditions are rarely met. Ease of maintenance and repair. If a component of a simple platform breaks, it's often straightforward to identify the issue and replace the faulty part with readily available alternatives. There's no need for specialized diagnostics or proprietary components. A broken leg on a simple table can be replaced with another piece of wood, often with minimal fuss. Versatility in application, from a simple table to a basic bridge, and even rudimentary machine components, the principles of simple platforms find diverse applications. Their adaptable nature allows them to be quickly reconfigured or repurposed for different needs, making them incredibly useful in dynamic environments or for rapid prototyping. However, the very simplicity that grants these advantages also comes with a set of notable cons. Limited load capacity, the most apparent limitation. A simple platform, relying on direct material strength and basic support, can only handle so much weight before it buckles, breaks, or collapses. There's no sophisticated load distribution or stress management at play. This restricts their use for heavy-duty applications or structures designed to withstand significant forces. Imagine trying to support a skyscraper with a wooden plank. It's simply not feasible. Lack of precision and control, simple platforms offer very little in terms of precise movement, controlled response, or intricate functionality. They are static or, at best, offer very basic, uncontrolled motion. If you need a platform that moves smoothly, elevates precisely, or adjusts to varying conditions, a simple design will fall far short. This limits their application in areas requiring automation, fine manipulation, or dynamic stability. Inefficiency and material waste. While seemingly cost-effective, simple platforms can sometimes be inefficient in their use of materials. To achieve a certain level of strength, you might need to use far more material than a more engineered solution would require, leading to unnecessary weight and bulk. There's often no optimization for material properties or stress distribution. Susceptibility to environmental factors. Without advanced engineering, simple platforms might be more vulnerable to environmental degradation. Wood rots, metal rusts, and basic joints can weaken under continuous exposure to weather or fluctuating temperatures. Their longevity might be significantly shorter than more sophisticated designs. Scaling limitations. As the size or complexity of the desired platform increases, the simple approach quickly becomes unmanageable or unsafe. You can't simply scale up a wooden plank to build a multi-story building. The fundamental assumptions about load distribution and material behavior break down at larger scales. Now, let's pivot to the Newtonian platform. This isn't just about using strong materials, it's about understanding and applying the fundamental laws of physics to predict and control how a platform behaves. It involves the rigorous application of Isaac Newton's laws of motion and universal gravitation, along with principles of statics, dynamics, material science, and structural analysis. Think of a modern bridge, a robotic arm, or a high-rise building. These are quintessential Newtonian platforms. The pros of a Newtonian platform are a direct counterpoint to the limitations of simple platforms. High load capacity and structural integrity. By precisely calculating forces, stresses, and material properties, Newtonian platforms can be designed to withstand immense loads and extreme conditions. Engineers can optimize the distribution of weight, reinforce critical points, and select materials with specific strengths, ensuring the structure remains stable and safe even under significant stress. This is what allows for massive skyscrapers, long-span bridges, and heavy machinery. With that said, thanks for watching, and until next time.